Hey, so welcome to 10.1 where we're going to be looking at the first derivative test. So I have a couple examples that hopefully will make this idea a little bit more clear for you. So first off, we're given the graph of a function f of x below, and we want to identify the following. So it's asking questions about the derivative of f of x. When is it greater than 0, which means when is it positive? When is it less than 0, which means when is it negative? And when is it equal to 0? So the first thing I would like to point out is that when you are looking at the derivative, it's the slope of the tangent line. So if we look at this, first off, I'm going to look at the slope of the tangent line here, 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 and here. Okay? Now, here's a couple of things that I notice is that when I reach a peak, I'm going to have a tangent line that has a slope equal to 0. So at this point here, my f prime of x, aka my slope, is equal to 0, which is the same thing that's happening here. So when I hit a peak or a valley, my derivative is going to equal 0 because the slope of that tangent line is 0. Now, if I look to the left of this very first peak, what is my tangent line here? Would it be positive or negative? Well, because as I look at it from left to right, it's positive. That means that my derivative is going to be greater than 0. Now, if I look to the right of that first peak, as I look at it from left to right, it's going down, which means it's decreasing. That means that it's going to have a negative slope, or a slope less than 0. And finally, if I look at this final interval, which is to the right of my second dip, that is increasing or moving upward from left to right, so that's going to have a slope greater than 0. So the intervals where f prime of x is greater than 0, whenever they give you a graph, what we're assuming is that the endpoints are going to continue in that fashion. So this left-hand side is going to go down forever, and this right-hand side is going to go up forever. So the intervals where my derivative is greater than 0 are going to be from negative infinity up to, well, up until I hit this x value, which is my peak, which is where the slope is going to change from being positive to negative, so it goes through 0. So negative infinity to negative 3, and it's also going to be positive again from this point 5 to infinity. See how from 5 to infinity my slope is positive? Now, where is my slope negative? It's going to be negative from negative 3 to 5. And at what points are my derivative equal to 0? Well, those are going to be these critical points, or these peaks and valleys, which are going to occur when x equals negative 3 and when x equals 5. So just one more time to reiterate, if we do the positive interval in pink, we're going to have a positive slope here and also a positive slope here. And if we do negative or decreasing in blue, we'll have a negative slope here. Okay, great. All right, so on the next one, we're going to use the diagram below, f prime, to determine something about the original function. So first off, what I want to say is that if we were looking at a graph of this function, what this is telling us is that between negative infinity to negative 3, my derivative is positive, which means that my slope would be positive, which means my function would be increasing. Between negative 3 and negative 1, it would be negative. That means that it would be decreasing. And between negative 1 and 2, it would also be decreasing. And from 2 to 4, it would be increasing. So what I probably have is a graph that looks something like this. Okay? The reason I kind of made it level out right here is because if they included negative 1, that probably means I have a slope of 0. Okay? So first, f is going to be increasing on these positive intervals. So it's going to be increasing here and and here. So I'm going to say it's going to be increasing from negative infinity until I hit negative 3, and 2 to infinity. The intervals where it's going to be decreasing are going to be from negative 3 to negative 1, and from negative 1 to 2. So negative 3 to negative 1, and negative 1 to 2. I don't want to include the negative 1 because since they have a little cutoff here, I'm assuming that the derivative either doesn't exist or is equal to 0, so I don't want to include that point. My function is going to have critical points at x equals negative 3, negative 1, and 2. So here are the other questions I might want to ask. Where does my function have a local maximum or an absolute maximum? I don't know. Where does it have a local minimum or an absolute minimum? And where does it have an inflection point? So a function is going to have a maximum when it goes from being positive to negative. So you can see as we go from positive to negative, we're going to end up having a peak here. So it's going to have a local maximum when x equals negative 3. It will have a local minimum when we go from negative to positive or decreasing to increasing. That's when we're going to have that valley. So that's going to occur when x equals 2. And an inflection point is when we don't change sign, but we do have a critical point there. So we can see that our graph goes down, levels out, and then keeps going down. This is called an inflection point. It's kind of like a leveling out point. So it's going to have an inflection point when x equals negative 1. Okay, great. Now for the next one, we want to use the function and its derivative to find each of the following. First, we want to find the critical points of our, I'm sorry, that should not be f prime, it should just be the original function f of x. So the critical points are going to occur when this function equals 0. So whenever our derivative is equal to 0, or keep in mind when it does not exist. So first off, when does our derivative not exist? Well, our derivative won't exist for x values we're not allowed to plug in. So if we look at this, I need to be worried about making the denominator 0. So it's not going to exist when x equals 0 because I can't divide by 0. The second question is, when does my derivative actually equal 0? Well, a function is going to be equal to 0 when the numerator equals 0. So that's going to happen when x to the 1/3 minus 2 equals 0, which means x to the 1/3 equals 2. So that's going to happen when x equals, so we have to cube both sides. That's going to happen when x equals 8. So we're going to have two critical points, one at 0 and one at 8. Just to give you a kind of overview, when you're looking for when the derivative does not exist, you're going to set the function equal to 0 and solve for x. Or I'm sorry. When you're looking for when the derivative does not exist, basically the only time you're going to be looking at that is when you have a denominator, and you're going to take the denominator and set it equal to 0, since you are never, ever, ever allowed to divide by 0. To find when the derivative equals 0, you're going to set it equal to 0. Now, if the derivative is a fraction, all you have to worry about is setting the numerator equal to 0. Now, the next thing we want to do is we want to determine if these critical points are maximums or minimums. So, to do this, what I like to do is I like to create a number line, okay? And then on that number line, I like to pick a number. So between negative infinity to 0, let's choose negative 2. Between 0 and 8, let's choose 4. And from 8 to infinity, let's choose 10. Now what I'm going to do with these is I'm going to plug them into my derivative. And let's say I take negative 2 and I plug it into my derivative. I just care if I get a number that's positive or negative. So if I take negative 2 and I plug it into my derivative function, what I'm going to get is I'm going to get a positive number. Now, if I take 4 and I plug it into my derivative, what I get out is I'm going to get out a negative number. By the way, if you want to know what these numbers actually are, if you take negative 2 and plug it in, it's going to give you 2.58, blah, 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 blah. If you take 4 and plug it in, you're going to get negative 0.259, da, 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 da. Now, if I take 10 and plug it in, what I'm going to get is a positive number. So that's going to give me 0.0716, blah, 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 blah. So if I look at this graph, what's going to happen is I'm going to have it increasing, then it will decrease, and then it will increase again. Notice that here I have a pointy part. That's because the derivative does not exist, so that means it's going to be a point. And here I have this smooth little valley here. That's because the derivative is equal to 0. So here, since I went from positive to negative, when x equals 0, I'm going to have a maximum. And when x equals 8, that is going to give me a minimum, since I'm going from negative to positive. So this is one way to check if you have maximums or minimums. I like to do this number line because it's very similar to the number line that we looked up at the example above. All right, so the next one we're going to do is the next one we're going to do is an actual application. So suppose that the average costs of a mining operation on the number of machines used and the average cost in dollars is given by this. Okay, so what we want to do is we want to find the critical values that lie in the domain. So when they say lie in the domain, because this is a real world problem, what they mean is even if you get a negative number, all of your values should be positive because you can't have a negative amount of machines. So if we want to find the critical values, we need to take the derivative of this function, or the average cost function. So the derivative of 2400x is going to be 2400. The derivative of this piece, you can rewrite that as 693,600 x to the negative first. So that's going to give you negative 693,6,000 divided by x squared. Okay, the reason that is because when you bring this exponent down in front, that's going to be a negative 693,6,000 x to the negative 2, and you can rewrite that x to the negative 2 as a x squared in the denominator. So we want to set this equal to 0, and then we want to solve for that x squared. So to do that, first thing I'm going to do is I'm going to move this 2400 to the other side, so it'll be negative 2400 equals negative 693,600 divided by x squared. Now this problem might look intimidating because it has an x squared in the denominator. Just go ahead and multiply both sides by x squared. As long as that x squared isn't 0, which it has to be strictly greater than 0, so we're okay, then we're not really breaking any math rules. So the left-hand side is going to become negative 2400 x squared, and that's going to be equal to negative 693,6,000. Now we're going to divide both sides by that negative 2400. So when we do that, what we are going to end up getting is x squared then has to be equal to 289. We're going to go ahead and take the square root of both sides, and we're going to get x is equal to 17. Now notice, because this is a real world example, we only want to include the positive 17 and not the negative. So our answer would be x equals 17. Alright, I was going to smash 10.2 into this video as well, which is going to be the second derivative test, but I'll save it for another video.